The APS has been a fantastic facility since it started in the mid-1990s. However, even in the early 2010s, it was clear that with advances in design technology, that massive increases in the performance of the machine could be realized.
Many light sources around the world were taking advantage of all the new technology that's been developed over the years and enhancing their capabilities, and we wanted to maintain that competitive advantage throughout the scientific community.
Some of the beamlines are going to see a 10,000-fold improvements in their sensitivity. So we're looking to upgrade all of the optics, all of the detectors to try to get the best possible science out for the scientific community.
It requires a massive change to the machine and the facility, and in our case, required removing 1.1 kilometers of the previous machine and installing a brand new 1.1 kilometer storage ring.
The Advanced Photon Source is one of the most powerful X-ray light sources in the world. Owned and operated by the U.S. Department of Energy Office of Science, the APS was built in the early 1990s at Argonne National Laboratory in Lamont, Illinois, and saw its first light in 1995. The APS is a giant X-ray microscope used by more than 5,000 scientists in a typical year to see deep into materials and figure out what they're made of and how they behave. APS experiments have led to stronger materials for roads and bridges, better batteries for electric cars, and more effective treatments and vaccines against diseases. The APS works by circulating electrons at nearly the speed of light, and this is the machine that keeps those electrons revolving and uses them to make extremely bright X-rays. It's called an electron storage ring, and it spans about 3/4 of a mile around. The upgrade project's goal was to replace this machine with one that generates X-ray beams that are up to 500 times brighter. To do that would require the work of hundreds of people and a shutdown of the APS for a full year.
I initially got involved with the APS upgrade in 2012. I came over from Fermilab. I had finished a couple projects there, and it was an opportunity to start another project, which fundamentally through my career is what I've loved to do, is to build things.
I had previous experience at Fermilab, and when Jim Kirby, he was the project manager at the time, came over to Argonne, he remembered my experience and thought that I could add value to the project. And so he recruited me to come over here and work on the upgrade project. So I've been here since 2012.
When you run a machine, you always think about what's your next machine gonna be. That's the job of the accelerator physicists at the facility. So when the project finally got funded, obviously the local accelerator physics group starts working on the physics of the design.
I think one of the biggest challenges we had when we were initially planning for the upgrade was figuring out how to handle the downtime. The priority is always to have Beam going to give users access to the facility so we can do the wonderful science that we do. And we wanted to minimize any impact to that community, trying to figure out what the length of that shutdown should be, how much could we actually accomplish in a given time frame. And then the second complication, I think, was just getting to the design. What was that machine going to look like?
In the mid-2013, 2014, the user community came out with a report working with DOE that suggested that the direction of the upgrade as originally envisioned wasn't the one that the user community thought would be best. And so in 2013-14, we made a change in the scope of the upgrade and basically replanned the whole thing. That's the upgrade we see now in front of us. It's a massive challenge. There had been 3 to 4 years of work that went into the previous design in the planning phase, in the design phase, and some R&D. And so it's hard to take something that has momentum and say, you know, we really need to address what our user community would like to do. And the way to do that is to change what we're doing as a whole.
Once there was agreement on that, I think some of the other pieces started to fall in place because now they had a framework to build upon. I came to work at Argonne in 2019 as an environmental safety and health coordinator, and I was assigned to work for the Advanced Photon Source upgrade. And over time, I've just taken on responsibilities as the lead. I think safety was the primary principle in planning for the shutdown. Looking at things and saying, okay, so here's where we want to end up. Here are some of the things that have to happen in order for it to get there. Now, how do we do all of that safely? And if you couldn't make all of those things mesh, then it was back to the drawing board to start the plant all over again.
The lead up to the shutdown included years of COVID and everything associated with that, years of supply chain disruptions, some due to COVID and other things, some due to economic conditions, and some due to war. And those aren't things you normally plan for. The ability of our team and our industrial partners to figure out solutions to every hiccup that came through was just brilliant. One of the huge advantages we had on the APS upgrade was that a good number of the staff that built the first upgrade were here to provide guidance.
My background is actually in metallurgical engineering. I had a bachelor's degree from University of Wisconsin. I ended up getting an interview for the first Advanced Photon Source, worked on the installation of the first machine, and then that transitioned to the removal and installation coordinator at APSU. The biggest difference, I think, between the two of them was that there was nothing there the first time. Everything was wide open. It was a huge green field. We come in the second time, and there's even after you take all of the old stuff out, there's still a lot of stuff left. It just makes it way more difficult logistically to be able to get everything installed.
Upgrading a facility large enough to fit Wrigley Field inside it is no small task. Even more difficult is building a new machine in the same tunnel as the original machine. In order to make this work, the upgrade team had to first remove the original electron storage ring piece by piece. At the same time, they had to assemble 1,300 magnets, thousands of components, and miles of cable into modules of the new storage ring, which they did at a warehouse facility called Building 981.
Building 981 was a completely empty building. We had to furnish it. We had to put clean rooms in, shelving, all kinds of things that once we got that infrastructure put in place, we started getting all the equipment in place to begin assembly.
For the module assembly process, that team did an amazing job. They outlined the procedures or the steps they wanted to take to assemble everything together. And they got everybody involved to make sure they fully understood the impact of the things they were doing and were being as careful as they could be. That many moving parts is always a challenge. So communication, making sure that everybody is communicating efficiently and timely with everybody that they need to, and the moving pieces are all going. That's always the big challenge. It's the day-to-day little things and not what you think are going to be the large challenges, because you plan those and you plan those and you plan those, and it's the little unexpected things that pop up that become the challenges.
Although it had been an incredibly hard multiple years to get the upgrade where it was, that was a point where, in fact, we had a bit of a celebration with our user community, celebrating the history of the APS and everything it had done. So as we started taking things out of the APS tunnel, it was a point of no return. It needs to come together.
I want to equate it to, if you ever ridden a roller coaster, right? When you first get in that seat and they buckle up that belt and you're like, I don't think I can turn back at this point. And we got to do it. Doing the shutdown, there were a lot of obstacles on that front, one of which were supply chain issues. The original plan was to have everything ready to go. So everything assembled, just sitting, waiting to be installed before we started the shutdown. We weren't able to achieve that, but we had reached a point where we thought the pace at which they were assembling modules was sufficient enough where when we started installing them, we could stay ahead of the installation teams.
And so we started the shutdown period with probably only maybe a third of the 200 modules ready to go. In that period, in 4 months, we had gone from something where we built maybe a module every week or 2 weeks to building a module a day. And so the team figured out not just how to build it, but how to do all the processing up front so that final assembly came together with tested parts in kits. It was like the world's biggest IKEA plant. You opened a box, every part you wanted was in that box. It was assembled to a procedure, it was tested to a procedure, and then we got on with the next one. I think it's one of the examples of how spectacular national labs can be with the right mix of people.
Basically, there's 40 sectors with 5 girders in each sector, so a total of 200 girders, each weighing, between 30 and 40,000 pounds. They all had magnets on them, and we removed all of that equipment.
Seeing the first pieces come out, I guess in the back of my head, there was this sort of insane idea like, if we really have to turn around now, we could figure it out. Now that was irrational, to be honest. It was out, it was over.
A few of us were worried about getting the first one out. And I kept telling all these guys, I'm like, the contractors have a plan. They know what they're doing. The first one came out, and then I was like, see, I told you.
For me, when things were coming out the tunnel, I was feeling, yes, get it out. I was ready for the new stuff to go in.
So one of the things that helped out immensely is that Brookhaven ended up taking all of our magnet modules. It was originally supposed to go to a landfill, but Brookhaven had a project that came along where the magnets were going to be useful to them. So we ended up packaging them up and shipping them over to Brookhaven, which saved, I think it was in the neighborhood of $3 to $4 million for us.
Seeing an empty tunnel was pretty incredible, actually. And taking a lap after everything was out of the tunnel was a bit breathtaking, actually. And then we had learned some things in those few months, too. We had learned the facility, being 30 years old, wasn't quite perfect as when it was built. It wasn't quite round. It wasn't quite flat. We had to do some engineering on the fly of how to deal with that and still put in the machine we wanted.
Once the original storage ring was removed from the tunnel, the new one had to be carefully assembled piece by piece. Each of the 200 modules was loaded onto a truck, driven to the APS, gently unloaded and maneuvered into place. The magnetic centers of each of these magnet modules had to be aligned with its neighbors to about half the width of a human hair. The process took 6 months to complete.
Watching the new storage ring come together and that first module go in, I think was a sense of relief as well as accomplishment. A huge sense of accomplishment, not just for me, but for the whole team. We were able to highlight other people, highlight the skills that they had, give people opportunities that they may not have otherwise had. I think that was the biggest part for me. Every time another module went in, there was a little sense of relief. And eventually we got to a point where I was like, I think we got this. I see this happening. You know, we only had a year to get everything done. There was some, I guess, excitement to get to the end point, but also a sense of, oh man, it kind of went fast. You know, did I take the time to actually enjoy it along the way?
Having given a few tours to various people, hearing somebody who has been a supporter of this for a long, long time come to you and be on a tour and say, you know, this is really beautiful. And I get it. This is not like a Monet. This is, but to some people it is actually. And I'm not sure I would have thought of it that way, but to hear somebody make a comment about it in that sort of a manner just makes you smile a little bit.
While the storage ring was under construction, an equally important part of the upgrade project was underway. The APS contains 72 experiment stations called Beamlines, where scientists make use of the X-ray beams for research. As part of the project, 7 new beamlines would be built and many others enhanced or improved to take advantage of the brighter beams.
I think the biggest challenge has been the scope of work that has come across for this project. We are not only installing an entire storage ring, but we're upgrading beamlines at the same time. I'm a mechanical engineer. I got my PhD in mechanical engineering. With the storage ring being upgraded, we want to make sure we're taking advantage of that new source with the brighter light and the tighter spot size. So our beamlines are being upgraded to take advantage of that using smaller optics and diagnostics, as well as more accurate measurement equipment and detectors.
A lot of these beamlines are 20, some 25 years old. We made improvements in optics, detector technology, and we're looking to really get the best possible performance for the scientific community. I've been working at Synchrotron since graduate school, almost 30 years now, working either as a user, a builder, beamline scientist. So for the APS upgrade project, I initially came on to build 1 beamline, then was asked to build 3 beamlines. And then as the project expanded, they asked me to sort of take over the installation and coordination of all of the beamline builds. For upgrading beamlines, we're looking at putting brand new infrastructure in. We're going to have new electrical, new high-speed networks, water cooling improvements, optics improvements. So we're looking to evaluate every beamline and figure out how to get the best possible performance out of that beamline going forward. detector technology has improved over the past decade or so. And you look at some of these detectors and they've got like 6 million pixels on them. And the resolution you could achieve, not only spatially, but also in the time domain is actually incredible.
So there's 72 beamlines that need to be installed at the APS, and we're trying to make sure that they all get installed correctly and accurately. We're placing things within 250 microns of accuracy, which is about 1/4 of a millimeter. It's very tight.
In addition to that, this team had to make sure they were realigning all the beam lines.
So the grand tube is a 3 meter in diameter, 22 meter long tube. It's a vacuum chamber that contains a detector in there. So we're moving those detectors along the length of it and across the span of it. So the installation of the grand tube took over 3 weeks of on-site installation. It started with the shipment of the grand tube segments in crates from Spain overseas, and we had to get them out of the crates, put them onto something that can roll them into the facility. The first segment gets installed, and then we align everything where it needs to be, then bring in the second segment and keep building off of there until we get everything together. And then making sure all the internals are installed correctly, and then pumping down and making sure we're able to bring that down to a vacuum level that's sufficient for our x-rays. Just seeing it come together, seeing an installation where it's like, this is something that is huge and has taken up so much time and resources for all across the facility. You're taking a lot of pride in your work at that point, and it just makes you feel good on the inside.
Once the new storage ring was in place, a dedicated team of accelerator physicists began to put it through its paces. Storage ring commissioning started in April 2024, and within days the first electrons were circulating in the new machine.
Preparation for commissioning took a lot of time, and we had a lot of time. When the production was going, that was our time to prepare for commissioning. There are things that you will need, and you write software to solve some particular problems. And then you just sit and think, what can go wrong and how can I fix it? The commissioning process is making things work. The accelerator is a very complicated installation, so there is a number of various errors. So commissioning process is going through these errors, finding them, fixing them, and moving forward. And it starts with testing without beam. A big team of engineers and technicians go around and check everything, and that's the stage where most of the errors are caught and corrected, and then after that we start operating with the beam. And beam is the ultimate measurement tool. It allows us to measure everything with extreme precision, and that allows us to move forward and find more errors and fix them, and on we go. Yeah, I know that from the outside it looked like a steady progress, but on the inside it was a flat process where you don't understand anything. Then it's a jump. When it's a breakthrough, then again a flat curve, nothing changes, everybody is pulling their hair out, and then again a breakthrough. So for us it's a staircase, and for people on the outside it's just a smooth progress. So we knew that this might happen, and we were ready for that, and that's part of the excitement of part of why we like this job. It's trying to figure out the things that you don't understand.
On June 17, 2024, the two halves of the project came together as the new storage ring delivered X-ray beams to the first of the APS scientific beamlines. In a site that has become commonplace at the APS as beamlines are brought online, the shutters were opened and brilliant light flooded in. With the storage ring working and beamlines in commissioning, it was time to celebrate. On July 17, 2024, federal and state lawmakers and U.S. Department of Energy officials joined Argonne to dedicate the new Advanced Photon Source.
So for the last 25 years, the Advanced Photon Source has produced great science that's helped the world all over, and seeing what the upgrade is going to do to enable new scientific discoveries, I think is going to be an amazing thing to just uncover over the next 25 years.
The potential, once the Advanced Photon Source is back up, is just incredible. And so I can't wait to see what walks through the doors.
So for me, the proudest moment is when we got this first X-rays back on the beamlines. So much work had been done over the past couple of years, and now to get those first X-rays back and the promise of that to the scientific community, it's very exciting to me. And I really look forward to hearing from the researchers in the next few months when they start to get results from their beamlines telling me that They're seeing something they've never seen before, and they're very excited about that to present the results to the scientific community.
I think as a team, we worked well together. Otherwise, this would have never worked, specifically in the time frame that they wanted. And when you get done, that last piece that came in, I was like, wow, this is it. It's finally over. It was a satisfying feeling, I'll tell you. It was incredible.
One of the glories of the APS and any light source is that almost immediate impact. And so when I say I look forward in the future to reading a weekly update on things, it is on that sort of a time scale. And it does impact the world around us in a very immediate way. And I think that's something that I'll look forward to doing, and knowing I played a small part in helping make that happen.
I mean, this is the greatest thing I made until hopefully August when I have my first child.